Hi, Akshya. Are you there?
Yes, sir.
Is there any exams going on?
Yes, sir. We have exams from Monday.
Monday. Okay. Fine. One second. We'll wait for 5 more minutes. Let us see if people are joining. All right. And then we'll see whether we're going to continue or not. Right. So till then, maybe if you have any doubts, you can ask me, Akshaya, Ashik, and Nanda. If you have any specific doubts on from any chapter, you can ask me in that time. In schools, have they completed your portions? All the chapters are completed?
Yes, sir.
Okay. 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 Hi people, very good evening. I think we'll start. Okay, so we have 5 people and we have already less things to complete. So once we complete this chart, maybe we'll wind up the class. Okay, right, let me share my screen. Coordination compounds, right? Okay, so last class I think we have completed your Werner's theory as well as your valence bond theory, right? We have seen everything. When we in weak field ligand, what will happen? Strong field ligand, what will happen? Pairing will happen, pairing will not happen. High spin, low spin, inner orbital complex, outer orbital complex, paramagnetic, diamagnetic, everything is our fingertips now, right? Okay, so there is only the last part of the chapter. So coming to that, we'll complete. I think we'll be completing it today, right? Okay, so the next theory, as I told you, there are various problems, right, with this what is that valence bond theory. Say for example, why what to say, why is it that certain ligands are strong, why is it certain ligands are weak is not given, is the explanation is not given, right? And in the presence of strong field ligands, why is it that the pairing happening is also not given, is also not explained, right? And the color of the coordination complexes, all I told you, 90% of the coordination complexes are going to have color, right? Why do they have color is again not explained. Strength of the coordinate bonds, we understand the coordinate bond is there, everything is explained, but this bond is stronger, this bond is weaker, again that is not properly explained in the case of valence bond theory, right? So to overcome all this, right, scientists developed another theory, right? And that theory is what is called as crystal field theory. Right? So the questions will be coming maximum from this only, like either from valence bond theory or IUPAC naming or the crystal field theory only. You'll be getting a lot of questions. Okay, so in short form, this is also called as CFT. Okay, crystal field theory. All right. Okay, so here what are we going to do? There are certain assumptions which are made in this theory. Okay, so the first few assumptions let us understand, right? So what he said, I mean, what crystal field theory says is that the ligands, right, ligands and the central metal atoms, right, ligands and the central metal, right, are considered as point charges, right? You know what do you mean by point charge, right? Point charge means a charged particle which does not have any volume. Say this is having a plus, this is having a minus, something like this. Okay, so when I say a point charge, means that particular thing does not have any volume, right? That is what you mean by a point charge. Positive, negative is okay, depending on the ligand and the central metal atom. Positive and negative will keep on changing. Okay, now next thing what it considers is that all interactions, right, all interactions, right, between your central metal and the ligands are purely electrostatic, right, or purely electrostatic. Okay, what do we know? What do you mean by electrostatic force, right? The Coulombic force. I can even write purely Coulombic. Means what? I know positive and negative will have a strong force of attraction. Like they say that the ligand and the central metal atoms are going to have only these kind of strong electrostatic forces of attraction. It is purely electrostatic. Okay, right? Okay, these are all the assumptions first you have to understand, which have been assumed in crystal field theory. Okay, right. Okay, and okay, after that, right, what it says is that the d orbitals, right, the d orbitals of the metal are degenerate, right? The d orbitals of the metal are degenerate in the absence of the ligand. The absence of ligands, right? What do you mean by degenerate? Degenerate means they'll have same energy. Okay, so what is it trying to say is that, say we have your 5 d orbitals, right? What are the 5 d orbitals? We have dxy, dyz, dxz, dx squared minus y squared, and dz squared. These are all the 5d orbitals, right? So all of them will have same energy in the absence of the orbitals. Okay, in the absence of the orbitals. Okay, right. Now, when the ligand is approaching, when ligand approaches, right? When ligand approaches, the energy of all the orbitals increase, of all the d orbitals is increased. That's another thing, right? So what are we trying to say? Say if I have a plot of energy, okay, this is energy, okay, on the y-axis, okay. Say now, initially in the absence of the d orbital, in the absence of the ligand, all the 5 d orbitals are having this much energy, okay, right? This is in absence of the ligand. Right now, when the ligand is present, what is going to happen is these orbitals, all the 5d orbitals energy are going to increase now, right? This one is in the presence of the ligand, or I would say at least the ligand is approaching, the ligand is near, not exactly in the full presence. Ligand is coming near, it is almost in the verge of making a bond, right? So ligand approach. Right. So when the ligand is totally absent, all the 5d orbitals are degenerate. Degenerate means they will have same energy. Right. Now, when the ligand is approaching, still they have the degeneracy is there. That means all of them are going to have same energy, but the energy value now you have seen, right? It is actually going to increase. Right. The energy value has increased for all the d orbitals, all the 5d orbitals. Is it not? Okay, that is next thing, right? Next, what is going to happen when the ligand is fully approached, right? Next point is, one second, guys. I don't know who's calling. Okay, sorry, people. Right. Right. So the next point is, now we understood that when the d orbitals, I mean the metal does not have any ligand, all the d orbitals degenerate and they have lesser energy. Right. When the ligand approaches, the energy of all the d orbital increases, but degeneracy is still there. Degeneracy is maintained. Right. Next, what is going to happen when in the presence of the ligand, in the presence of ligands, right, the degeneracy is lost. Right. In the presence of the ligand, the degeneracy is lost. Right. What do you mean by that? That means when the ligand is completely there, when they are there with the metal atom and they are forming the bond, right? All the d orbitals are not going to have same energy. Some of them are going to have higher energy. Some of them are going to have lesser energy. We will try to understand how. Okay. From this point, we'll try to understand how. Right. So all the points here I have mentioned should be there in your fingertips. First is the ligand and metals are considered to be point charges. All the interaction between the metal and the ligand are going to be purely electrostatic. And next thing is the d orbitals is, I mean, the metals d orbital are going to be degenerate and they're going to have lesser energy in the absence of the orbital, in the absence of the ligand, right? But in the presence of the ligand, when the ligand is approaching, what is going to happen? The degeneracy is still maintained, but all the d orbitals energy is now increased, right? And after that, when the ligand is fully present, then what is going to happen? The degeneracy will be lost. Okay. Now, how the degeneracy will be lost is going to depend upon two things: whether it is going to be an octahedral complex, right, or whether it is going to be a tetrahedral complex. And obviously, it is going to depend on square planar complex also, right? But how the degeneracy is lost in case of square planar complex is not in our syllabus. Okay, we have octahedral complex. as well as we have tetrahedral complex. How the degeneracy is getting lost, that we'll see. But for square planar complexes, we don't have it in the syllabus. Okay, right. So fine. Let us now take octahedral complexes. Right, octahedral complexes. Okay, right. Now, what we have to understand is, in case of octahedral complex or in tetrahedral complex, first we have to understand what is the direction of ligand approach. Direction of ligand approach. Okay. Now, directions of ligand are very simple, right? What is the shape, octahedral shape? I have the metal, right? And we have ligand, 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 and here again ligand. Right? So hope you know how the shape looks, right? The shape will look exactly like a square bipyramidal. Like say, for example, if this is the metal center, right? All the four places you will have the ligand, top one ligand, bottom one ligand. That is exactly how it is going to look. Right? Okay. Now we know that all the bond angles here are 90 degrees. All the angles here are 90, 90, 90. Every bond angle here is 90 degrees. Right? So you can easily understand that the ligands are going to approach in 6 directions. Obviously, there are going to be 6 ligands, right? And all the 6 ligands are going to have 6 directions, right? What can be directions? Say X. I mean, if I talk in terms of coordinate axis, right? If we talk in terms of the coordinate axis X, Y, Z, right? You can have X, Y, minus Y, Z, minus Z. These are the possible ligand approach directions. Is it not? Right? So one will come like this, the other will come like this. X and minus X, one will come like this, the other will come like this. Another, this is Y, one will come like this, the other will come like this. Right? That is how the 6 ligands will approach along the XYZ direction. We can even tell that the directions of ligand approach is along the XYZ axis. Right? Is there any doubt here? I hope you can understand, right? All the directions, I mean, the ligand is going to approach in, approach along the axis, along X-axis, along Y-axis, along Z-axis, but again, positive and negative, both are taken into the picture. Right? That is how you will be able to form the structure. Right? That is how, say, for example, this axis is X-axis, this axis is Y-axis, this axis is Z-axis. Right? All of them will be mutually perpendicular. Right? Okay. Now, this we understood. Right? Now, if it is going to be purely electrostatic, we said that the direction, the interaction between your metal and the ligand is going to be purely electrostatic. Right? Now, it is not always that the electrostatic means it is only going to be only attractive force. I can even have repulsions. Is it not? Right? Now, you can understand, you can ask me here, right? Why is it that the energy is first of all getting increased? Right? For I have in the complete absence of the ligand, the d orbitals are having lesser energy, right? But when the ligand is approaching, all the d orbitals energy is first of all increasing. Why is the question? Now, the energy of all the d orbitals are increasing because of repulsion. Repulsion between what? Repulsion between the d electrons and the ligand electrons. Right? The ligands are going to have some electron. The d orbitals are going to have some electrons. Is it not? So there is going to be huge repulsion between the d orbital, that is metal's d orbital. You can even write, this is not d, this is metal's d orbital. Okay, the metal's d orbital electron and the ligand's electron are going to have repulsion happening between them. Right? That is the reason why the energy of the orbitals are increasing. Here I have no force. Right? Here I have no repulsive force, nothing, no attractive force also there. But when the ligand is approaching, right, because of the repulsion between the electron present in the metal and between the electron present in the ligand, we are going to have increase in energy. Right? Okay. Now, when the ligand is very properly approaching in all the possible directions, right? Now, what we have to understand is, I told you that the degeneracy will be lost. Right? Degeneracy will be lost. Now, for us to understand how the degeneracy is going to get lost, let us try to understand what are the shapes of the different orbitals. Okay, so we will see shapes of all the d orbitals. Right? So whichever d orbital is going to have the electrons which are in the direction, say for example, the ligand is coming like this, in the direction only the d orbital is also there. right? Then what will happen? I will have more energy, right? There I'll have more repulsion happening. Again, I repeat. So the ligand is coming like this, or say the ligand is coming in this direction, right? And the d orbital is also along this direction. So obviously the electron here and the electron here will have so much repulsion, the energy will be far more increased, right? But say the ligand is approaching like this, the ligand is approaching like this, and say the d orbital is somewhere, something like this, right? Or say something like this, cross, right? It is not exactly in the path of the ligand, right? Now, I will have repulsion. I cannot say that the repulsion will not be there, but definitely compared to the previous case when the ligands and the d orbital were like this, right? Compared to this case, now when I compare it here, what is going to happen? Here I'm going to have lesser repulsion compared to the previous case, because here they are very closely attracted, we are very close to each other. Here they're a little far apart, right? I hope that makes sense to you, right? So if I can understand what are the shapes of the d orbitals, I will be able to get a better picture. Okay, now how does dxy looks? Does I understand now, right? So, right, this is your y orbital, this is your x orbital, say for assuming, right? So I know the shape is going to be like this, right? The shape is going to be like this. Okay, right. Now, and in the case of dy z, what is going to happen? Right, here we have, right, this is your y-axis and say this is your z-axis, right? Now the shapes are same, but except that the what is that? Except that the axis is different. Here it is x and y, here it is y and z, right? Okay, next we can go for dzx or dxz, whatever it is, right? So here also you'll have the same shape, but your axis will be different. Say this is your z-axis, this is your x-axis, right? So now we will have a shape like this, again double shape. Okay, right. Now dx squared minus y squared is going to look like this. Okay, this is your y-axis, this is your x-axis. Now okay, this is how it looks. Okay, now the difference between these three and this one, okay, I will draw the next one also, right? That is your dz squared, right? Dz squared, how it looks. Okay, this is our z-axis. Okay, this can be x or y, doesn't matter. Okay, now we are going to have one lobe like this, and surrounding this we are going to have a ring like this. Is it not? Right? So now if you check the first three, right, the lobes, that I mean the lobe, this is what is called as one lobe, this is called as another lobe, right? There are 4 lobes on all of these, right? In all of these 4 cases we have 4 lobes except for dz squared. Like dz squared is a little different, right? Generally d orbital will have 4 lobes, right? So what can I see in the case of dxy, yz and zx, right? The lobes are pointing, right? The lobes are pointing in between the axis, in between your axis. Now can't you see, this is your y-axis, this line is a y-axis, this is your x-axis line, and the lobes are pointed in between x and y-axis. Again, this also in between x and y, in between x and y, in between x and y. Right? Same way, if I check dyz, this is your y-axis, this is your x-axis. Again, what you see, the lobes are pointed in between your axis. Same goes with z and x. This is z-axis, this is x-axis. Again, what you're seeing, the lobes are pointed in between our axis. Right? But here, if you check for dx squared minus y squared and dz squared, the lobes are pointed along the axis. Right? The lobes are pointed along the axis. This is your y-axis. Along the axis, we have a lobe. Along the x-axis, we have a lobe. Again, along the y-axis, along the z-axis, along the x-axis. Right? Now here also what I see, along the z-axis, you have a lobe. Along the z-axis, you have a lobe. Right? So that is the difference between your first 3, that is dxy, dyz, and dzx. That is first part. The other part is that we are going to have dx minus y squared and dz squared, where the lobes are pointed along the axis. Here for the first 3, the lobes are pointing towards the axis, sorry, in between the axis, right? In between 2 axes, right? Okay. Now this we understood. right? And I told you the directions of ligand approach, right? The directions of ligand approach are here. X, along Y, along Z. Right now, I told you if you have a smaller distance, or say the d orbitals are going to be placed in the direction of the ligand, I am going to have more repulsion and more energy will be getting for the d orbitals. Right, more repulsion means the energy of those particular d orbitals which are going to be in the path of the ligand is going to have more repulsion and they will have more energy. Okay, so think about it. If I ask you, out of these, say this is one set, this is set one, okay, and this is set two. Okay, now which set of orbitals will have higher repulsion with the ligands? Think about it and tell me your answer. You need not be right, you need not be wrong. Put your answer in the chat box, people. Right, which set will suffer more repulsion when the ligand is approaching? Right, think about it and put your answers in the chat box. Go for it. Right, whether it's set one, that is dxy, y is zx, or whether it is going to be set two, which is comprising of dx1 minus y squared and dz squared. Right, which will suffer more repulsion when the ligand is approaching. Now we have 8 people. Good. Go for it, people. You need not be right, you need not be wrong, it doesn't matter. Just tell me what you think. Which will have more repulsion? Okay, set one is going to have more repulsion. Anandita says set one is going to have more repulsion. Okay, fine. Everybody, go on, participate. Don't make me call you names. Go for it. Okay, Rohan says set one. Fine. Go on. Everybody. Jaya, Anirudh, Devesh, Ashik, everybody, go on. Okay, fine. Let us try to understand what exactly is happening. Right now, people, right? So what we understand is, say for example, if I take dxy, for example, we take dxy, right? Now, what is the direction of ligand approach? The direction, let me use black color, right? The black color represents your ligand approach direction. The ligand is approaching like this, like this, like this, like this. That is along the axis, along x-axis, along y-axis, along z-axis, along xy axis, basically. Okay, now here also what is happening? This is the direction of ligand approach. 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 Right? Same way here. This is the direction of ligand approach. 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 Right? Okay. Now, because as I told you, it is going to be along x, y, z axis. That is only then you will be able to form octahedral structure. Right? Okay. Now, in case of here, again, the ligand direction is going to say along the axis. This is one direction, another direction, another direction, another direction. Same way here. This is there. This is direction. This is direction. This is the direction. This is the direction. Right now, you see, right, where are the lobes pointed exactly in the direction of the ligand? Again, repeat the question. Where are the lobes of the d orbitals pointed exactly in the direction of the ligand? Can someone answer? Where are the lobes of the d orbital? In which d orbitals the lobes are pointed exactly along the direction of the ligand approach? Where? Which orbitals?
dx square, y square, and dz square.
Absolutely. Is it not? Now already the lobes are pointed along the axis. The ligand is also approaching in the same directions. Right here also it's the same. The lobes are pointed along the z-axis, and again along the XYZ directions, you are seeing that the ligand is approaching. So where will I have more repulsion? Obviously in these sets, in these two, more repulsion will be there. right? In these two, more repulsion will be there because the lobes are pointed exactly in the direction of the ligand approach, right? Okay. Now, obviously, in this case, repulsion will be there, but compared to this case where the lobes are pointed along the axis, here the lobes are pointed in between the axis. So here, lesser repulsion will be there. Right here, lesser repulsion will be there. Okay, right. Now, what happened now? What we understood is, right, when the ligands are not there at all, the energy was less, degeneracy. Okay, when the ligand is approaching, all the d orbitals are going to have energy increased, right? But now, out of these three, two of them are going to have more repulsion. Other three of them are going to have lesser repulsion. So the two which are going to have more repulsion is going to have more energy, right? And the three which are going to have lesser repulsion is going to have lesser energy, right? Okay, so how the diagram is going to look, you see how the energy diagram will look like. This is how it is going to look like, right? This is your energy, right? Now the ligands and the 5d orbitals are having, this is absence of ligand, right? When the ligand is approaching, all the d orbitals increase in their energy. This is when the ligand approach is there, right? Now, when the ligand has completely approached, we know how it is going to look, right? Now, two of the orbitals are going to have very high energy, right? Let me write it somewhere else. This ligand approach, right? Let me write it here. Now, this is your ligand approach, right? Now, when the ligand is completely there, two of the orbitals are going to have very high energy because their lobes are pointed along the axis, right? Now, obviously, the other three orbitals are going to have little decrease in energy, right? And because they are going to have lobes pointed in between the axis and they suffer lesser repulsion, so lesser energy, right? And we know what are these orbitals now. This orbital is nothing but dx squared minus y squared, and this is dz squared. And what are these? This is nothing but dxy, dzx, and dyz, right? So that is why we told that the degeneracy is lost. What is degenerate? What do you mean by degenerate orbitals? Orbitals having same energy. Now you understand that 5d orbitals were degenerate, all of them having same energy value, right? But now the degeneracy is lost when the ligand is completely present. When ligand is completely present, right? Okay, that is what happens in case of octahedral complexes. Anybody has any questions, please ask me. Any doubt, whatever be the doubt, please ask me. Is there any question anybody wants to ask? Okay, I hope that everybody is following, everybody is clear how exactly the degeneracy is lost. Why is it that the dx squared minus y squared and dz squared is having higher energy, and why is it the other three orbitals having lesser energy? I hope that is understood.
Yes, sir.
Right, good. So now, people, we are going to call these orbitals as in the name of a set. I told you, right? This, where is it? Yeah, this is one set, right? This is set number 2, and this is another set we called it, right? So this set, that is the lobes, the d orbitals having lobes pointed in between the axis, those things are going to be called as T2G orbitals, or it is also called as T2G set. Okay, right? And obviously here the second set, which is having the lobes pointed along the axis, right? Those one are going to be called as EG set. Okay, or EG orbitals. Okay, so when we say EG consists of this dx minus y squared and dz squared, and T2G is going to contain dxy, dyz, and dzx. Right? Okay, so we can even write it here. Where is it? Right? So these two set of orbitals are your EG set, and these three orbitals are your T2G set. Okay, right. Now, between these two, right? I mean, obviously there is an energy difference between this and this, right? Right? Between this and this, there is some energy difference. Is it not? Right? Now that energy difference is denoted by the letter del O. It's not, right? This O is not, this is O. O represents octahedron. Right? O represents octahedron. Right? So this this particular what is that energy difference, right? This is what is called as how to put it, the energy barrier, or we can call it actually, okay, fine, right? This energy difference is what is called as your energy barrier. Okay, or this has little more technical term which we can use, right? This energy barrier can also be called as crystal field splitting energy. Crystal field splitting energy. Okay, now this energy difference between the EG set and the T2G set is what is called as crystal field splitting energy. Okay, now you will study another thing. Okay, you will study crystal field stabilizing energy also. That we'll see later. That is a difference. See, when I say CFSC, right? CFSC is the short form. CFSC is crystal field stabilizing energy. Okay, remember that. That is different. I'll tell you how to find that out. Okay, CFSC is crystal field stabilizing energy, but for this we don't do this. We don't use CFSC. This is crystal field splitting energy. Okay, but even though the acronyms will come out to be same, right? Don't confuse yourselves. When I say calculate CFSC of a molecule, so and so, I give the problem. You have to calculate the crystal field stabilizing energy. That we'll see later how to calculate that. Okay, but this one is different. This one is nothing but the energy difference between your EG set and the T2G set. What is the energy difference between these two? Del naught, we represent it. Okay, this difference, right, is what is your del naught. Okay, right. Now another thing is this one, right? Right. So between from this point, this and this are not equal. Okay, but I'm talking about this and this. Okay, now these two energy differences, that is from the average energy to the EG set and from the T2G set to the average energy, these are not equal. Please understand that first. Okay, these are not equal. Again and again I'm repeating, this value, this gap and this gap are not same. That means it is not exactly like 50-50%, right? Actually what happens is this is a little clumsy. Let me draw another diagram for you. Right, so 5d orbitals, right? Now their energy is increased, right? One is going to be the EG set, right? Let me write it on the top here. Right, one is your EG set and the another one is your T2G set, right? So now overall is del naught. That's okay. Right, but I'm talking about this distance and this distance. Okay, that these two distances are not same. Actually, this is going to be 0.6 del naught, right? And this is going to be 0.4 del naught. Okay, overall it's del naught. That means 60% gap is here and only 40% gap is here. That is what I'm trying to say. Okay, 60% gap is here, only 40% gap is here. Okay, that is a 0.6 and 0.4. Total, if you add what? 0.6 plus 0.4 totally will become 1 del naught. Right? Anyways, that's what I'm trying to tell you. The distance between the average to the T2G or EG is not same. Okay, the distance from the Barry center, okay, this particular point, right? This particular point is what is called as your Barry center. Okay, this particular point is what is called as your Barry center. Anyways, from the average value to the EG is 0.6 del naught. From the T2G to the average value is 0.4 del naught. Okay, fine. Now, people, right now, okay, how do I start this? No issues. Right now, I told you that there is something called as CFSC. Is it not? There is something called as CFSC, crystal field stabilizing energy. Okay, now that has a formula. What formula? It is equal to number of electrons in T2G, right? Number of electrons into T, or let me write it like this, right? Minus 0.4 del O into number of electrons in T2G. Okay, and this is I'll what is this? NT2G means number of electrons in T2G orbital plus, right? 0.6 del O into number of electrons in Eg. This is the formula for CFSE. Okay, you can even write it here. This is equal to your CFSE. Right? And what is this? A number of electrons in T2G is, NT2G is number of electrons in T2G set, right? And this one is number of electrons in EG set. Okay, right? NT2G is number of electrons in T2G, and EG is number of electrons in EG. Okay, we will do a lot of problems on this. Don't worry about this. Okay, right. Now, how do we calculate, right? How do we write the configuration now? Right now, whenever they ask you to write the configuration for the d orbitals in case of crystal field theory, you should write in terms of T2G only. Right? Now you can easily understand T2G set can have a maximum of 6 electrons. Is it not? Because there are 3 orbitals. But 2 can be placed here, 2 can be placed here, 2 can be placed here. Right? And same way, your EG set can have a maximum of 4 electrons. No issues because there are only 2 orbitals there. 2 orbitals can be placed here, 2 orbitals can be placed here. Right? That is also understood. T2G can have a maximum of 6 electrons, and EG set can have a maximum of 4 electrons. Done. Right? Okay, if that's the case, let us see how do we write the configurations. Right? For example, when I have a d orbital configuration of d1, other things are there, don't worry about it. Right? Other orbitals are there, don't worry about it. I'm talking only about the d orbital in the metal, right? The 3D or 4D, whatever it is. Okay, so when I write d1, when the configuration is d1, right? How do we write the configuration in terms of T2G and EG? It's very simple. We can write, obviously, right? We have to follow Aufbau's principle. What is Aufbau's principle? Aufbau's principle says that we have to fill the electron in the lower energy orbital first, then only you have to go for the higher energy orbitals. Is it not? Right? We have to go for lower energy orbital first, then only we have to go for electron filling in the higher energy orbital. So obviously we know T2G is going to have lower energy and EG is going to have higher energy. Is it not? So we should write T2G1, EG0. Because in EG obviously there will be no electron. Say for example, D2 we go. Right? Again, I told you this can have a maximum of 3 electrons, right? Okay. Now we can even put it like this. We have T2G3 and 3 orbitals, and EG has 2. There is only 1 electron here. Okay, right. Now, when I go for D2 configuration, obviously we have to write it as T2G2. That is in the T2G orbital, 2 electrons will be there, and EG will have 0. Is it now? Right. Okay. Now, how do we represent it? We will represent it like this. T2G is having 3, EG is having 2. Right. Now, is it correct? What I'm writing is correct? Can I write it like this? In T2G2 orbitals means this is how I should write. Is it correct? Okay. How many of you, again, let's take a quiz, right? Let's take a vote. How many of you people say that this is correct? Or how many of you people say that this is going to be wrong, sir? We should write it in some other way. Correct or not? Just put it in a chat box. Again, you need, it doesn't matter whether you're right or wrong. Okay, just go to the chat box and put your answers. This way of writing T2G2, EG0, 2 electrons like this, is it correct way of writing or not? Go for it and put your answer in the chat box. Yeah, this is what I'm telling. Yes, is it correct or not? Go on, guys, go on. Don't think so much. Right? Is it correct or not? You just have to put yes or no. Go on, it doesn't matter. Nobody is going to judge you whether it is going to be correct or not correct. I mean, your answer is going to be correct or not correct. Doesn't matter. Okay, Niklesh says no. Anandita says wrong. Okay. Anybody else wants to contribute? Okay, fine. Anandita or Niklesh, any reasons you thought that, okay, this is not correct. Any particular reason, or it was just a guess, sir?
I think you should fill it one by one, right? Because in the same place you can't put two electrons.
Correct. What you're telling is absolutely right. There is one name of a rule, right, which you have to follow. What is that rule?
Principle.
Hund's rule.
Polys is different. What is the other one? Afba we already saw. Polys you are done. So what is one more remaining? What is the one thing which is remaining?
Hund's rule, right?
Hund's rule. Yes. Right. What Hund's rule says? Hund's rule says that whenever you are filling electron in degenerate orbitals, it works only for degenerate orbitals. That means orbitals having same energy, right? So whenever you're going to fill electrons in the degenerate orbitals, all the degenerate orbital has to be singly filled first. And once you have singly filled all of them, then you can go for pairing, right? Okay, once you have filled them single electron in all the degenerate orbitals, then if you have more electron, then only you can go for pairing, right? So this is not right. Okay, how we should write is like this. Okay, right, fine. Moving on, D3. Okay, D3, how do we write? T2G3, again Eg0. Is it not? Right, again, how do we write this? 1, 2, 3, 1, 2. So here again, you have to follow Hund's rule. Third electron will go here only. Right, okay. Now, D4. Right, D4. Now, I have, now there's a problem, right? Right, where should I put the 3? Where should I put the 4th electron is the problem. There are two possibilities. Let me see. Right, for D4, there are going to be two different possibilities. One is like this, T2G4 Eg0. You can put the electron in the T2G itself. No issues, right? How do we put this? I can put 2 electrons here, 1 electron here. Now the pairing can happen because all the degenerate orbitals are filled, right? Or you can do this thing also, right? You could have written T2G3 Eg1, right? T2G3 Eg1 you could have written, right? So now how the configuration will look? 3 orbitals here, 1 electron, I mean two orbitals here, 1, 2, 3, 4th electron is going here, right? Now which is correct, which is not correct? Both of them can be right, both of them can be wrong depending on the situation. Okay, both of them can be right or both of them can be wrong depending on the situation. What is the situation?
It
Right.
depends on
Now,
the ligands, no, sir?
It depends on the
Ligands.
Yes, it depends on the ligand. Yes, absolutely. Right, we'll see how exactly this is going to happen. Right, okay. So what we have to understand is there are two kinds of energy which you have to look for. One is what is called as our pairing energy. Right, one is what is called as our pairing energy. Right, now what is pairing energy? Pairing energy is the energy required to overcome repulsion of electrons and pair them. Yes, is it not? I have, for example, if I already have electron in one box. Okay, now if I want to place one more electron coming like this, obviously these two will suffer a lot of repulsion. Is it not? Because both are electrons only, both are negative charges. Is it not? Right, now if at all I have to place them, I have to push the electron, I have to push the second electron, then only it will go and get paired. Right, now in that pushing you're spending some energy, isn't it? You are pushing it against the repulsion, right? You are pushing the electron against the repulsion. That there is spending amount of energy there, is it not? Now that energy is what is called as our pairing energy. Okay, so it is not a letter P. Okay, capital P we write for denoting this pairing energy. Okay, it's very easy to understand. Energy required to overcome the repulsion of electron and pair them. What is the energy required is what is called as the pairing energy. Okay, right. Next one, right? Next one is your crystal field stabilizing energy, splitting energy. Right, we are talking about crystal field splitting energy. Right, this is nothing but your del O. That is how we represent it, right? Basically, the difference between this, right? The difference between your Eg and T2G, this difference is your del O. I'm talking about that difference, right? Now, depending on that, right, obviously we'll be able to, that exactly is what is your crystal field splitting energy. We know what to say, CFSE. CFSE is different. CFSE's formula is different, right? This del O is your crystal field still splitting energy, but if at all I apply this formula completely, then it becomes CFSE, crystal field stabilizing energy. Okay, well, anyway, solve problems on it, don't worry. Okay, right. So depending on which is going to be higher, which is going to be lesser, then these two configurations are going to come. Right now, obviously, one can be higher, one can be lesser. There can be only two possibilities, right? One possibility is pairing energy greater than del O, right? Pairing energy is greater than the del O. Basically, the electron is going to find it so difficult to pair itself because I'm going to have so much repulsion, right? And the del naught is very simple. So between the EG and between your T2G and your EG, there is only small difference. So the electron can easily go here. Right? The electron can easily go here and occupy the EG set rather than getting paired. Right? That is not going to happen because the pairing energy is very high. Right? So the pairing energy is very high compared to your del naught. What we can easily understand, pairing will not happen. Pairing will not happen. Right? And I can say that the electron is going to go to EG. Right? Because pairing will not happen, it can now it will try to do whatever is minimum energy expenditure. Now, not only in this case, anything which happens in chemistry, we have to keep only one thing in mind, that we need to go for minimum energy expenditure. Right? Okay. Now, in which way we can go for minimum energy expenditure? Obviously, instead of pairing, if I can put the electron in the EG, that is where I spend minimum energy. So that's what will happen. Right? So I can easily tell that this particular case will happen. T2G3 EG1 will happen if the pairing energy is greater than del O. Right? If the pairing energy is greater than del O. Okay. Right. Obviously, now the second case is where the pairing energy is less than a del O, or say the del O, the difference between this and this is very huge, right? Now, obviously, the pairing energy will be very less compared to this, right? So obviously, the electron will not be able to shift from T2G to EG. That is very difficult because I'm going to spend a lot of energy on this, right? Rather, it is going to just spend little energy and get paired, right? So here, pairing will happen. Pairing will happen, right? And obviously electron will stay in the T2G orbital only, right? Okay, so we can easily say that this one, right, this one will happen if the pairing energy is lesser than del O, or say the del O is greater than the pairing energy. Only then this kind of thing will happen, rather than going to the EG, which is going to be very difficult. The electron will spend smaller energy and get paired. Okay, right. Now, people, what we have to understand is the pairing energy is a constant value. This is not going to change because everything is electron only. They will have same amount of charge. So whether you're going to pair for one pairing, you're going to have some amount of energy spent, right? So this is a constant value, right? But this del O is a variable, right? Depending, or say, or how to put it, say whether I'm going to take complex number 1 or complex number 2, the pairing energy is not going to change. Right, that is going to be constant because we're just talking about electrons, right? But this del O will definitely depend on what kind of complex are we speaking about. Complex 1 and complex 2 will have two different values of del O's. Okay, right. So what you have to understand now is what are the factors affecting del O, right? What are the factors affecting del O, right? Now, first main factor is the strength of the ligand, right? Strength of the ligand, right? Now, more and more is the strength of the ligand, more and more will be the splitting. Okay, more and more strength of the ligand, more and more will be the energy difference, right? Say, for example, if the ligand is ammonia, for example, or say, let me take something very similar. If the ligand is Cl minus, right? Now, the energy difference between that will be very small. But say if the ligand was Cn minus, then the difference in energy is very high. Okay, why? Because we know Cn minus is a strong field ligand, right? Whereas your Cl minus is a weak field ligand, right? So stronger the ligand, larger the splitting. That is one criteria, right? Okay. Now, second criteria is going to depend upon the oxidation state of the metal. Oxidation state, oxidation state of the metal, right? And again, in this case, it is going to be directly proportional to del O, right? Now, why is it like this? If you ask me, more and more oxidation states, say +2 and +5 will compare, assuming, right? +2 and +5. This is having lesser positive charge. This is having higher positive charge. We are talking about attractive force and repulsive forces, right? So if I'm going to have more amount of charge, I'm going to have more amount of attraction, more amount of repulsion. At the end of the day, there is going to be more splitting. That is how it is going to happen, right? So the oxidation state of the metal is also going to play a role in deciding your del O. Right? That means, say for +2 oxidation state of the metal, we are going to have only small difference, right? But for +5, we are going to have a huge difference in the with the energy difference between your Eg and T2G, right? Okay. Third thing and the final thing, right? The del O of 5D series elements. I'm talking about the metal, right? 5D elements will have more splitting than your 4D, than your 3D. Okay, say for example, I have to think about any element. Say for example, if I want to compare nickel, cadmium, what are the three elements under nickel? Nickel, cadmium, and one more thing, right? Can you look at the periodic table and tell me nickel? I forgot. Or say any other thing. Oh, okay, we can take this one. I remember this. Copper, silver, gold. We can take. Right? Copper, silver, gold. This belongs to 3D. Then this belongs to 4D. This belongs to 5D. Say for example, we are talking about Cu NH3 4 times plus, right? And say we are talking about Ag NH3 4 times plus, and say we are talking about Au NH3 4 times plus, right? Now the ligands are same. NH4 only, right? The amount of positive is also same. This is Cu plus, Ag plus, and Au plus. All are plus one oxidation states, right? But now what are we seeing? This is in 3D, this is in 4D, this is in 5D. So definitely this is going to have maximum del O, right? And this is going to have minimum del O. Okay, right? So like this also you will be able to tell which is going to have higher del O, which is going to have lesser del O. Okay, so these three are the criteria, right? The strength of the ligand is going to be directly proportional to the del O value. Oxidation state of the metal is again going to have, it is going to be directly proportional to the del O value. And obviously the del naught is going to be higher for 5D elements than 4D than 3D, right? Okay, these three are the only simple criteria. Very simple. Okay, right. Now, this is the most important point, right? This is the most important point here, because other things you're not going to, like at least for your level, for CBSE level, you're not going to deal so much with your oxidation states and all. But yeah, this is going to be very, very important. Okay, right. Now, if you understood this point, we can understand why pairing happens, right? Why pairing happens in the presence of strong field ligands, right? We saw in case of VB theory that if at all strong field ligands are there, then I have to go for forced pairing. Weak field ligand is there, no problem, right? Why? Because of this reason only. When the strong field ligands are there, the del naught value is so high, so high that it is going to be greater than the pairing energy. And obviously we know what is going to happen if we have pairing energy to be lesser than del O. That is where del O is greater than P, means that the electron will not be able to shift to the higher energy, rather it is going to go and get paired. Okay, so that is the reason why we saw that in case of strong field ligands, pairing should happen, right? Everything is connected now. I told you that you will be studying about the reason for this pairing, why pairing is happening in your crystal field theory, and here is the reason for this. Okay, right? Fine. Now, that is about your factors affecting del O, right? So accordingly, you will be putting your this thing. Accordingly, you will be putting our what is that? Configurations T2G and EG. How many electrons will be there? All of them will be done, right? Okay. Now,
Excuse me, sir.
yes, come on, tell me.
Will you just show the second factor one?
Second factor, yeah.
Thank you, sir.
Okay, right? Anybody has any other questions? Okay, I suppose everybody is following, right? Good, fine. So now maybe we'll do some problems, right? Based on this. Coordination compounds. Hold on, people. Hold on. I'll be back in 1 minute. Okay. I did not get the book which I wanted, but still I have a book. No problem. who don't have CFSC. Okay. Right. So maybe you don't have, like, did you study about this particular formula in your school? Did you study this formula, people? This formula, did you see in your school?
No, sir.
Can you check in a textbook whether this formula is there?
No, sir.
It's not there?
No, sir, I don't think it's there.
Okay, then what? Then don't worry about it. Maybe this is only for JEE and NEET. Okay, fine. Then it is very easy. Okay, then crystal field stabilizing. I mean, then CFT is very easy. Okay, fine. So can you calculate? I have CO F6 3 minus, right? Can you calculate the magnetic moment using CFT? Right? We know what is magnetic moment. Magnetic moment formula also we know. Right? Magnetic moment formula is what? Root of n into n plus 2. Isn't it? Root of n into n plus 2. Right? Fine. Now we know what is this n also. N is the number of unpaired electrons. Right? N is the number of unpaired electrons. Okay. Now, for this particular molecule, can you calculate what is the magnetic moment? Go for it. All that you have to do is find the CFT configuration. In terms of T2G and EG, you have to find the configuration and then decide this. Maybe this problem I'll help you. Okay. See, cobalt is now, if you check X minus 6 equal to minus 3, X is going to be in plus 3 oxidation state. Cobalt is actually going to be in plus 3 oxidation state. No issues. Okay, right. Fine. So if it is going to be in plus 3 oxidation state, CO, I think it's nickel cobalt, or it's cobalt nickel. So it is going to have 4s2 or say 3d7 4s2. No issues. Is it not? This is the configuration, right? 3d7 4s2. Is it correct? Guys, can you confirm? So it is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, correct. Okay, this is correct. 3d7, 4s2. Okay, right. Now we say it's having cobalt 3 plus. Right? We are saying that we're going to have cobalt 3 plus. Right? That means 2 electrons from here, 1 electron from here is removed. All that we have is 3d6. Correct. All that we have is 3d6. Correct. Okay. So if you have 3d6, you have to write in terms of T2G and EG. Right? You have to write this in terms of T2G and 3G. So we are going to have T2G and EG. Right? So let me draw the orbitals. 1, 2, 3, 1, 2. Right? Now we have to decide what kind of ligand we have. We understand F minus is a weak field ligand. Right? We understand that what is that? This is going to be weak field ligand for all weak field ligand, right? You can actually write it here also. Where are you? Right? So for this will happen, right? When the pairing energy will be greater than the del O for all weak field ligands. Obviously, because why? Because we understand that the strength of the ligand is directly proportional to del O, right? So strength of the ligand is directly proportional to del O. If I'm going to have weak field ligand, then they'll have very less strength, they'll have very less del O. Obviously, it is going to be lesser than what? It is going to be lesser than your pairing energy. Okay, so pairing energy will always be greater than del O for all weak field ligands, right? And here, this will happen when pairing energy will be, or say the del O will be greater than the pairing energy for all strong field ligands. Okay, right? We have to remember this. That means for weak field ligands, pairing will not happen. The same thing only. For weak field ligand, pairing will not happen. For strong field ligand, pairing should happen. That is all that we have to understand. Okay, right. So Where is the question we are trying to solve? Yeah, right. We have 3d6. Okay, so first 3 electrons here. Okay, right. Now I know F minus is there, which is a weak field ligand, so no pairing. Right, no pairing will happen. So if we can, instead of pairing it, we can go over the EG. So 1, 2, and how many electrons are filled? 1, 2, 3, 4, 5, and now we can come back to this 6. This is the configuration. Okay, this is the configuration we are going to have. All right. Now we can easily calculate what is the magnetic moment. Right. Magnetic moment is equal to root of n into n plus 2. Now, how many unpaired electrons you have? 1, 2, 3, 4. 4 unpaired electrons. 4 into 4 plus 2. Right. 4 into 4 plus 2 will be root of 4 into 6. That is root of 24. That's it. That's the answer to this question. Right. And you have to write the moment unit. Unit is BM. What is BM? Can someone tell me what is BM? What is BM?
Bohr's magneton, sir.
Bohr magneton. That's the unit of magnetic moment. Okay, right? This is how you answer the questions, right? If weak field ligands are there, don't go for pairing. If strong field ligands are there, then go for pairing. As simple as that. Okay, and again, I can ask you, talk about the magnetic behavior in this question. Obviously, it is going to be what? It is going to be paramagnetic because it is having unpaired electrons. Because we know for substances to be paramagnetic, we need to have unpaired electrons. If all the electrons are paired, then we are going to have diamagnetic species. Right? Okay. Fine. Now say, let us do this. Another question we'll do. Right now, this time, let me see. You can do this. Right. Say we have FeCN 6 times 4 minus. Again, same thing. Tell me about the magnetic moment of this quadrular species. Right.
So it's a 2 root 6, sir.
I don't know. We'll check. Okay. Anybody else is getting the answer? Same answer. 2 root 6. I don't know. If you tell me the overall thing, it's, I think, overall what? Root of 24, like this, what you got?
Oh, yes, sir. Root 24 is what I got.
Oh, again, root 24 only. Okay. Fine. Right. Anybody else is getting to root
I
24?
might be wrong, sir. I'm not sure.
Yeah, no issues. No issues. Well, anyways, check. I'm just asking, anybody else got root 24? Okay, fine. Let us check. So here, I first will calculate the oxidation state. Right, oxidation state is X. Cn minus is there, so minus 6, right, is equal to minus 4. So X is going to be in plus 2 oxidation state. Is it not? Right, X is going to be in plus 2 oxidation state. Right, and we have Cn minus. Cn minus is a strong field ligand. We know this. Right, Cn minus is a strong field ligand, so here pairing has to happen, right? Okay, so we know iron is going to have, I think it's scandium, titanium, vanadium, 1, 2, 3, 4, 5, 6, so it's 3d6, right? So iron is going to have 3d6 4s2. right? Okay, now what we have is Fe2 plus, right? That means this electrons are gone. So here in this case, we have 3d6, right? Okay, now again, we have to write it in terms of T2G and Eg, right? T2G and Eg. Now
That
we
will be
have
zero, no, sir. Because all the
Yeah.
6 electrons are
Yes.
there, so 3 will pair.
correct, right? So first we'll put 3 electrons, single electrons. Now again the question comes, pairing will happen or pairing will not happen. Now that depends on the ligand, right? Ligand is a strong field ligand, so obviously pairing should happen. Now all the 3 more electrons will go here only, right? So what is the number of unpaired electron? Number of unpaired electron is 0. So magnetic moment is 0. Right? This is how the questions will be asked. Right? All that we have to understand is find the oxidation state, right? And see what ligand we have. If at all we have a strong field ligand, go for pairing. If weak field ligand is there, no, don't go for pairing, go to the Eg orbital. Okay, maybe we'll do another question. So that this time I think you'll be able to get. Okay, so we have again why cobalt, something else. Okay, Cr H2O 6 times 3 plus. Okay, for this find the magnetic moment. Now H2O is strong field ligand or weak field ligand?
Weak field, sir.
Weak field. NH3?
Strong fields.
Yes, right. Both of them are actually intermediately strong field ligand. But if at all NH3 is asked, then we'll go for strong field. If at all H2O is given, then we'll go for weak field. Okay. Fine.
So here also I'm getting good 24. So
Okay, I will check. Right, so it's chromium. So it is first H2O is a weak ligand, weak field ligand. That is the first thing you will notice. Right? Okay. Now what we have Cr, and okay, Cr it's +3 oxidation because H2O doesn't have any charge, neutral ligand. Right? Okay. So we have Cr to have 3D. It's actually going to be what? It's actually going to be 3D5 4s1. This is how we write generally, right? It should be actually 3D4 4s2, but for half field stability, we write it like this, right? 3D5 4s1. Okay, no issues. Now we are going to go for Cr3 plus, right? So Cr3 plus means 1 electron from here, 2 more electrons from here. So it is going to become 3D3. No issues, right? So all that we'll have is, right? We have to write in terms of T2G and Eg. So 1, 2, 3, 1, 2, right? Now we have only 3 electrons here, right? There is no question of whether I'm going to have strong field ligand or weak field ligand. I have only 3 electrons, and those 3 electrons have no choice than to go for your T2G set. Because the 4th electron, if it was there, if it was 3D4, for example, then I would have put the electron here, but nothing of that sort is going to happen. Right? Because here I have only 3 electrons to be filled. So don't worry about it. Right? This electron. What is wrong? Okay. Right? So if it was 3D4, I would have put the electron here. I would have put the electron here. Right? But it's only 3D3. So that's it. So now you have to calculate the magnetic moment. Magnetic moment is root of n into n plus 2, and n is equal to 3 here. So 3 into 3 plus 2, right? That is basically 3 into 5, right? So root 15 Bn is the answer to this question. Very simple, right? All that you have to do is find the number of d orbitals electron and put them in T2G and EG, and you are set. Done. Okay, I hope everybody is following. Everybody understood
I
this.
have a doubt, sir.
Yeah, tell me.
What type of questions will they ask from CFTs? Only these type questions?
Yeah, only these kind of questions they'll ask. They'll ask you whether, like they might even ask you to write the splitting diagram, like how we draw the splitting diagram, right? This one, the graph which I showed you. Where is it? This kind of diagram they might ask you to draw, right? And say they might ask you to find the magnetic moment, paramagnetic behavior, everything in terms of your this thing, crystal field theory, right? These are the only questions possible, right?
Okay, sir.
Okay, we still have tetrahedral complexes left, right? That will finish in the next class, and I'll be completing your this thing also. What is that? Metal carbonyls also I'll complete, right? And I'll be starting your next chapter from the next class, right? So which chapter you want? Any suggestions? Next chapter?
Chemical kinetics, sir.
Sorry?
Chemical kinetics.
Okay, fine. Is everybody okay? Chemical kinetics? I'm okay. Are you guys okay?
Okay.
Yes.
Okay, cool then. So next class, that is I think on Sunday's class, we'll be starting with chemical kinetics. Okay. Right, people. Thank you so much. We'll again meet on Sunday.
Thank you, sir.
Thank you, sir.
Thank you, sir.